Welcome students in the lecture series of some basic concepts of real analysis. In the previous lectures, we discussed about algebraic properties of real numbers and sequences of real numbers, subsequences, quasi-sequences and their convergent. In this lecture, we will discuss about the limit concepts. So, let us start with the limits. Mathematical analysis is generally understood to refer to that area of mathematics in which systematic use is made of various limiting concepts. In this preceding lectures, we studied one of these limiting concepts, the limit of a sequence of real numbers. In this section, we will introduce the important notion of a function. The intuitive idea of a function f having a limit L at point C is that the value f of x are close to that number L when x is approaching towards C, but note that this must be different from C. Again, the intuitive idea of a function f having a limit L at a point C is that the value f of x are close to L when x is close to C, but this is different from C. But it is necessary to have a technical way of working with the idea of close to, and this is accomplished in the epsilon delta definition. We need to note that in order for the idea of the limit of a function f at a point C to be meaningful, if it is necessary that f be defined at point near to C. If it need not be defined at the point C, but it should be defined at enough points which are close to C. Now, to understand better, let us start with the basic definition of cluster point. Let A be a subset of a real number R. A point C belongs to R is a cluster point of a set A if for every delta greater than 0, there must exist at least one point x belongs to the set A which is different from C such that modulus of x minus C is less than delta. This is our definition of cluster point. I repeat the definition. Let A be a subset of a real number R and a point C belongs to R is a cluster point of A if for every delta greater than 0, there exists at least one point from the set A and which is different from C such that we have modulus of x minus C is less than delta. The definition is rephrased in the language of neighborhoods as a point C is a cluster point of the set A if every delta neighborhood which is defined as V delta with respect to C is equals to C minus delta and C plus delta of C contains at least one point of A which is distinct from the point C. We note that the point C may or may not be a member of the set A, but even if it is in A, it is ignored when deciding whether it is a cluster point of A or not, since we explicitly require that there be points in V delta C intersection A distinct from the point C in order for C to be a cluster point of A. For example, let A is equals to the set 1 comma 2. Then we can say that the point 1 is not a cluster point of the set A, since if we choose delta is equals to 1 by 2 which gives a neighborhood of 1 that contains no point of A distinct from 1. The same result is true for the point 2. So, we conclude that the set A is equals to 1 comma 2 has no cluster points. Let us start with some basic results which are based on cluster points. Our first result is, our statement says that a number C belongs to the real number R is a cluster point of a set A which is a subset of R if and only if there exists a sequence an in the set A such that we have limit of the sequence is equals to C and we have an is not equals to C for all n belongs to the natural number. Let us repeat the statement. A number C belongs to the real number R is a cluster point of a subset A which is a subset of R if and only if there exists a sequence an in the A such that we have limit of that sequence is equals to C and we have an is not equals to C for all n belongs to the natural numbers. Let us start with the proof. As given, C is a cluster point of the set A. Then for any n belongs to the natural number, we can say that by the definition of a cluster point, there exists a delta neighborhood. In this case, we take 1 by n neighborhood of C, which contains at least one point an in A, but this point is different from C. So, by the definition we can say that an belongs to A and an is not equals to C and we have modulus of an minus C is less than delta, and in this case we choose delta is equals to 1 by n. Hence, by the definition of convergence we can say that our limit of the sequence an is equals to C. Conversely, if there exists a sequence an in A minus singleton C with limit of an is equals to C, then for any delta greater than 0, there must exist some k such that for all n greater than or equals to k, we have an belongs to the delta neighborhood of C. This is by the definition of convergence. Therefore, the delta neighborhood V delta C of C contains the point an for all n greater than or equals to k, which belongs to the set A and which are distinct from the point C. For example, let us start the example which emphasizes that a cluster point of a set may or may not belongs to the set. Our first example is open interval I is equals to 1 comma 3. In this open interval, every point of the closed interval 1 comma 3 is a cluster point of I. We must note that the points 1 and 3 are a cluster point of the interval I is equals to 1 comma 3, but they do not belong to the open interval I. Another example for this, let A is equals to 1 by n for all n belongs to set A. The set A has only the point 0 as a cluster point. Again, we note that none of the point in the set A is a cluster point. The geometrical interpretation of a cluster point is, geometrically you can imagine a point C as the cluster point of a set A. If for any open interval you draw around C, that interval always contains at least one point from A that is not C itself. This means you can find points of A getting closer and closer to C without ever reaching it. Now, let us start with the definition of a limits of a function at a given point. We now state the precise definition of a limit of a function f at point C. It is important to note that in this definition, it is immaterial whether f is defined at C or not. In any case, we exclude C from consideration in the determination of the limits. Now, let us start with the definition of a limit of a function at some given point C. Let A be a subset of R and a point C is a cluster point of A. Now, let us define a function f from a set A to real numbers, and a real number L is said to be a limit of a function f at given point C if for any given epsilon greater than 0, there must exist a delta greater than 0 such that if x belongs to A and modulus of x minus c is less than delta, then we must have modulus of f of x minus L is less than epsilon. I repeat the definition of a limit of a function at a given point. Let us say A be a subset of a real numbers and let a point C is a cluster point of the given set A. Now, define a function f which is defined from A to real numbers, then a real number capital L is said to be a limit of a function f at point C if for any given epsilon greater than 0, there must exist a delta greater than 0 such that if we have x belongs to A and 0 is less than modulus of x minus c and modulus of x minus c is less than delta, then we must have modulus of f of x minus L is less than epsilon. We note that the value of delta depends on epsilon. Will sometime write delta depending upon epsilon instead of delta to emphasize the dependence of delta. The inequality 0 is less than modulus of x minus c is equivalent to saying that the point is distinct from c, that is x is not equals to c. If L is a limit point of a function f at a given point C, then we also say that the function f converges to L at point C, and symbolically we write limit x approaches towards C, f of x is equals to L. We also say that f of x approaches L as our x approaches to C. As we can see in the diagram, the geometrical interpretation of the limit is that the input x approaches a specific value, say c, on the real line. The corresponding output f of x of the function approaches to a single specific value L. It means that the points on the graph get arbitrarily close to a specific point c comma L. Even if the function is undefined at C itself, the limit exists only if the function approaches the same value, say L. From the both side, either x is less than C or x is greater than C. Let us start with some theorems related on the limits of a function at given point. So, our first result is if for a function f which is defined from A to R and C is a cluster point of A, then the function can have at most one limit at C, or we can say that the function f can have only one limit point at a given point. So, let us start with the proof. Suppose that the function f defined from A to R have two limits at a given point C. Say L1 is limit and L2 is also a limit of a function f at point C. Recall the definition of a limit of a function at a given point. Let A be a subset of R and let a point C is a cluster point of A. For a function f which is defined from A to R, then a number L is said to be a limit of a function f at point C if for any given epsilon greater than 0, there must exist some delta greater than 0 which is depending upon our epsilon, such that if we have x belongs to A and modulus of x minus c is less than delta, then we must have modulus of f of x minus L is less than epsilon. In this case, we say that L is a limit of a function f at point C. Now, using this, we can say that for any epsilon upon 2 greater than 0, there must exist some delta which is depending upon epsilon upon 2 which is greater than 0, such that if x belongs to A and modulus of x minus c is less than delta which is depending upon epsilon upon 2, then we must have f of x minus L1 is less than epsilon by 2. Say this is our equation number 1. We can say that L1 is the limit of f at point C when our delta is depending upon epsilon upon 2. In similar way, we can say that for L2 also, so for any epsilon upon 2 greater than 0, there must exist delta dash again which is depending upon epsilon upon 2 which is greater than 0, such that if we have x belongs to A and modulus of x minus c is less than delta dash which is depending upon epsilon upon 2, then we have modulus of f of x minus L2 is less than epsilon upon 2. Say this is our equation number 2, and in this case we say that L2 is a limit of a function f at point C where delta dash is depending upon epsilon upon 2. Now recall the statement 1, our first equation is modulus of f of x minus L1 is less than epsilon upon 2, as L1 is a limit of f of x at point C, and from equation 2 we can say that L2 is a limit of a function f at point C. Now choose delta is equals to minimum of delta which is depending upon epsilon upon 2 and minimum of delta dash which is again depending upon epsilon upon 2. So, our delta is equals to minimum of these two deltas, then if x belongs to A and modulus of x minus c is less than delta, we now consider modulus of L1 minus L2. If we add f of x and subtract f of x, we get modulus of L1 minus L2 plus f of x minus f of x. The triangular inequality implies that modulus of L1 minus L2 is less or equals to modulus of f of x minus L1 plus modulus of f of x minus L2 from equation number 1 and equation number 2. Our equation number 1 is modulus of f of x minus L1 is less than epsilon upon 2, and our equation number 2 is modulus of f of x minus L2 is less than epsilon upon 2. So, substituting these values in this equation, we get modulus of L1 minus L2 is strictly less than epsilon upon 2 plus epsilon upon 2 which is again equals to epsilon. Hence, we get modulus of L1 minus L2 is less than epsilon, as we know that epsilon greater than 0 is an arbitrary number. So, we conclude that L1 minus L2 is equals to 0, hence L1 must be equals to L2. So, we can say that if a function f defined from A to R and C be a cluster point of A, then the function f can have only one limit at point C. Next statement is, let f be a function from A to R and C is a cluster point of A, then the following statements are equivalent. Our first statement is, limit x approaches towards C, f of x is equals to L. That means the limit of a function f at point C is equals to L. Then given any epsilon neighborhood V delta L, there exists a delta neighborhood of C such that if x is not equals to C, is any point in the V delta neighborhood of C intersection A, then we can say that f of x belongs to the delta neighborhood of L. For example, we need to prove that limit of modulus x is equals to modulus of C when x approaches towards C. Now, recall the definition of a limit of a function at a given point. Let A be a subset of R and a point C is a cluster point of A, then we say that a number L is a limit of a function f at point C if for any given epsilon greater than 0, there must exist some delta greater than 0, such that equation number 1 hold and modulus of f of x minus L is less than epsilon. Now, using this definition and consider this equality, modulus of f of x minus modulus of c, as we know that f of x is equals to nothing but modulus of x. So, we get modulus of mod x minus mod c. This is nothing but we can write as this equality is less or equals to modulus of x minus c. Say this is our equation number 2. Now, choose in this case delta is equals to epsilon. If delta is equals to epsilon and x belongs to R and mod of x minus c is less than delta, then from equation number 2 we can conclude that this equation is less than delta and we chose delta is equals to epsilon. So, we get modulus of f of x minus mod c is strictly less than epsilon, that is modulus of f of x minus mod c is less than epsilon. As again epsilon greater than 0 is an arbitrary number, we conclude that limit of mod x is equals to mod c as x approaches towards c. Let us consider another example. We need to prove that limit of under root x is equals to under root c when x approaches towards c and c must be greater than 0. Now, again recall the definition of a function, a limit of a function at given point. If a function is defined from a to a real number capital L is said to be a limit of a function f at a given point c if for any epsilon greater than 0 there exists a delta greater than 0 such that if x belongs to a and 0 is less than mod of x minus c and mod of x minus c is strictly less than delta, then we must have f of x minus L is less than epsilon. In this case, we say that L is a limit of a function f at a point c. So, using this we get modulus of f of x minus root c is equals to under root x minus root c. After rationalization, we get mod of f of x minus root c is equals to modulus of under root x minus under root c into under root modulus of under root x plus under root c upon modulus of under root x plus under root c. After solving this, we get modulus of f of x minus root c is equals to modulus of x minus c upon modulus of under root x plus under root c. Say this is our equation number 1. Now, we can say that root x plus c is greater than root c. If we take reciprocal, then we get our equation number 2, that is 1 upon under root x plus under root c is strictly less than 1 upon under root c. From equation number 1 and equation number 2, we get modulus of f of x minus root c is equals to modulus of x minus c upon under root x plus under root c, which is strictly less than mod of x minus c is less than under root c. From equation number 2, we can easily check 1 upon under root x plus under root c is less than 1 upon under root c. So, if we replace 1 upon under root x plus under root c to 1 upon under root c, we get our equation number 3. So, equation number 3 is modulus of f of x minus root c is less than modulus of x minus c upon root c. Now, in this case, we choose epsilon, we choose delta is equals to epsilon into under root c. Now, consider x belongs to R positive, or we can say that positive real numbers, and mod of x minus c is less than delta, which is depending upon epsilon, and in this case we choose delta is equals to epsilon root c. So, substitute this value in the equation number 3. Our equation number 3 is modulus of f of x minus root c is less than modulus of x minus c upon root c. So, if we substitute the value of mod of x minus c in this equation, we get modulus of x minus c upon under root c is strictly less than epsilon root c upon root c. Hence, we get is equals to epsilon. So, from equation number 3, we get modulus of f of x minus root c is less than epsilon. As epsilon greater than 0 is an arbitrary number, we conclude that limit of under root x is equals to under root c, where x approaches towards c, where c is strictly greater than 0. Hence, in this case the limit is root c, where x approaches towards 0. Further, we will discuss in the next lecture. Thank you.